Merry Christmas, everyone, to the best holiday of the year. If for some reason Christmas isn't your favorite holiday, then I don't know if we can be friends. Um, but anyways, today we have a Christmas themed-ish sort of math problem where we have that Reindeer Street has 2025 houses in a row, numbered 1 through 2025, 1 through 2025, and they all have Christmas lights hung outside because it's Christmas. And all the lights are initially on, and the Grinch, trying to ruin Christmas, walks down the street 2025 times, and on the nth walk, toggles the light of every nth house. So, the first walk, he'll toggle the light of every house. Second walk, every other house. Third walk, every third house, and so on. And toggle meaning if the house lights are on, then he turns them off, and if they're off, then he turns them on. And we want to determine at the end of the 2025 or 2025 walks which houses will end up with their lights off. And so I guess trying to sort of draw this out with examples for, let's say, the first 10 houses. All right, we have that they are all initially on. I guess I'll use green for on and red for off. And let's say day. This will be day 0 initially. So day 1, the Grinch will go through and toggle the lights of every single house. So he just turns them all off. Day 1, or day 2, sorry, he will toggle the lights of every other house. So in this case, every even house, even numbered house, and then the odd ones he'll ignore. On the 3rd day, he'll toggle the lights of every third house, so multiple of 3. That's the 3rd house, the 6th house, and then 9th house. And then everything else stays the same. And then I guess we'll do 2 more days. For the 4th day, you'll toggle the lights of every 4th house. So that's day 4 and day 8. And everything else stays the same. And then on the 5th day, you'll toggle the lights of every 5th house. So that's day 5 and day 10. And everything else, again, stays the same. And so, is there any pattern in that we can see so far? And I guess the only houses that we can really look at are the first 5 houses, right? Because on the 6th day, we have to start at the 6th house. 7th day, we have the first house we toggle will be the 7th house. And so we'll never touch any of the first 5 houses ever again, right? So what we have here is set in stone. And so which houses do we have that are off, right? So day 1 is off, or house 1 is off, and house 4 will be off. And even though it's only 2 houses, you might, postulate that, 1 is 1 squared, 4 is 2 squared. So maybe, you know, after all 2025 walks that the Grinch makes, all of the houses with perfect square numbers will be the houses that are turned off. And then the other houses, the ones that aren't perfect squares, will have their lights still on. And so now that we have this hunch, we want to prove this or show this more rigorously. And the way we can do that is we can just look at a particular house, right? Let's say house N. And we want to determine on which, or like how many times will the Grinch, toggle the lights of this house. So on which walks will house n be toggled? And what we can realize is house n will only be toggled on the walks where the walk number divides the house number, right? So because I guess we can see on walk 1 you'll toggle every house because 1 divides every number. On walk 2 you toggle every other house, so it's every even house, and 2 divides every even house, or every even number. On the third walk you toggle every third house, so that's 3, 6, 9, so that's every multiple of 3. So we can indeed conclude that house n, for house n, the number will be toggled on each walk, let's say d, such that d divides n. And so this implies number of times that house n is toggled is equal to the number of divisors of n. Right, so now, how do we find the number of divisors of n? Guess one way to do this is to look at the prime factorization of n, right? If n is equal to p1 to the e1, p2 to the e2, all the way to pk to the ek, right? This is a prime factorization. Then we have that the number of divisors based on this is actually just e1 plus 1 times e2 plus 2 times e3, oh sorry, not plus 2, plus 1, e3 plus 1, all the way multiplied to ek plus 1. And the idea behind this is for every prime factor, right? For every divisor, every divisor's prime factorization has to be also in some form a1, p1 to the a1, p2 to the a2, all the way to pk to the ek, and we have that 0 is less than or equal to ai is less than or equal to ei for all I. Yeah. And so, like, let's say for this first prime, that means a1 can take up values from 0, 1, 2, all the way to e1. So there's e1 plus 1 choices for what a1 could be, and that's what we have here, right? And then, but we also have that each, prime is independent of each other. So the number of ways we can choose a2 is independent from the number of ways you can choose a3, is independent, all the way to the number of ways you can choose AK. This should be A, yeah. And so that means we just multiply the number of ways we can do this and end up getting this formula here. And so remember, we had our hunch that, it's the perfect squares whose, lights will be off at the end. So I guess what does that mean for a house to have its light off at the end? Because it starts on, all the houses have their lights on in the beginning. Having them off at the end means that they were toggled an odd number of times, right? And having them still on at the end means they were toggled an even number of times. So we want to show that this, let's call this number of divisors of n. We'll call this, I think, is it v? It might be v of n. We want to show that v of n is odd for squares and even for non-squares. And the idea is, if n is a perfect square, then in its prime factorization, right, all of the powers are even. Then e1, e2, all the way to ek are even. So that means e1 plus 1, e2 plus 1, all the way to ek plus 1 are odd. And so their product must also be odd as well. Right, so if n is a square, we do have that this is odd, right, which is what we want to find. And so it will be toggled, or house n will be toggled an odd number of times, and thus have its light be off at the end. On the other hand, right, if n is not square, then one of these powers, right, has to be odd. So if n is not squared, then one of e1, e2, let's say it's ei, then ei plus 1 is even, so the product e1 plus 1, e2 plus 1, right, some ei plus 1 in the middle, and then ek plus 1 is even. So if n is not squared, this is equal to v of n, right, the number of divisors. If n is not square, then the number of divisors is even. And so house n will be toggled an even number of times and thus still stay on after the Grinch finishes walking. And so you can conclude that all houses with perfect square numbers will be off at the end. And in particular, those are 1, 4, 9, 16, all the way to 44 squared and 45 squared, which is exactly 2025. And yeah, that's it.